Diastereomers. Diastereomers are stereoisomers but are not superimposable. They are not superimposable. So you can have diastereomers when a molecule has two or more stereogenic centers. Again, and of course you may have, this may or may not be chiral. We will see that in a second. So what do I mean by this? If I just were to just draw a simple molecule, this has two stereogenic centers. There's one right there. I'm going to make it blue, and there's one right there. Each carbon is attached to 4 different groups. The H's are not shown. Right here. So this has the possibility of having stereoisomers, and it may or may not be chiral, depending on, again, on the stereoisomer. However, let's look at an example of what's the maximum number of stereoisomers that we can have if we have multiple stereogenic centers. Well, the formula is simple. You always take 2 to the n. N is the number, again, n is the number of stereogenic centers. Or stereocenters. Okay, let's look at this and determine how many stereogenic centers we have. Remember, stereogenic centers means 4 different groups, 4 different groups. And the H's may not be shown, remember, in skeletal structures. So I'm going to use blue to show them. Can you find, if you'd like to pause and try it and see if you have multiple, you may do so. Again, carbon with 4 different groups. Here we go, 1. I have 4, this one has 4 different groups. It has the N, it has this C with a double bond O, and of course, this ester group, and then of course, you have the benzyl group right here. The H is not shown, so here I'll show the H. Is this a stereogenic center? Nope, it's not a tetrahedral carbon, not a tetrahedral carbon. Yep. Even though they may be shown like this way, not all of them actually include these, the wedges, the hatched or the solid wedge. So just be aware of that. So there's another one. Where would the H be if this is going back? You guessed it, it would be the front. So we have 2 of them. How many possible stereo? Well, actually, we have more. Apologize for that. Yeah, we have 2. I'm sorry. We have 2. This one is not the stereogenic center because you have 2 H's attached to it, so be very careful. So you have 2. How many stereoisomers can you have? Well, you would say 2 to 2, and that would be 4 maximum stereoisomers, which could be enantiomers and diastereomers. So be able to trace where they are. Okay, so let's look at diastereomers. So as I said, diastereomers are stereoisomers that are not mirror images of each other, and therefore they're not superimposable. That doesn't apply, right? So let's look at 2-bromo-3-chlorobutane. It has again, it has 2 different stereogenic centers, 2 of them right there. So let's get used to drawing it this way, although sometimes students just prefer the other way. So here's the other way. What I mean by this is just like that. So you go. Let's start with the BR, and then we'll do the CL. And then they can do this. Etc. Now, this one helps. I use it all the time. But at first, you might want to get into the idea of using the tetrahedral because it's going to also help show you how they look like. So you have 4 possibilities in terms of the configuration. Remember, we have 2 stereogenic centers right here. So 2 to the 2, that would be 4. Again, 2 stereocenters or stereogenic centers. So that would be 2 to the 2, which is 4. That's the number of the maximum stereoisomers you can have. And the possibilities are the following. One can have R and the other one can have the R configuration. One can have S and the other one can have an S configuration. And of course, what would be the next one? Not saying that these are related here, is you would have an S and an R, and an R and an S. So let's look at this. Bromine would be 1, and this becomes messy, very messy when you start writing because you have to do both sides. Bromine would be 1. This group would be 2, not the CH3. This group would be 2. So I'll put a 2 here on the top. CH3 would be 3. And of course, 4 is the H. So it goes like this. I'm going to have to erase just to let you know because it's just going to be very messy. So that's what R on that C right there. So write that down because I'm going to erase and do the other one. It's just going to be too messy if you do both of them at the same time. So we said this was an R right here. You do this one. This is going to be 1 because we're doing this other stereogenic center. This would be 2. This would be 3. And of course, H would be 4. So what is that? That's also clockwise. So that's R. So you have R, R. Very well. Now, to save you the headache of going through each one of these, you just have to use a very, very commonsensical approach. And that is, just check if there was any switching in the bonds. We notice when we look at this one, let me erase these so that we're not confused. We notice that the Br was switched on this carbon right here, on the first carbon. So that would be an S. It's now in the back. Remember, one switch means what? You switch the configuration. Also, the Cl was switched, so that's an S. What about here? Compare. This is the same as that, so that will be S. And this one is back to where we wanted it. So that would be what? An R. Or you can compare to the original. Just compare to the original. There was a switch, so this must be the opposite, S. There was no switch on this one, so it must be the same, which is R. And now compare this carbon to this. You see the Br is in the same position, no switch, so that remains R. And of course, this remains This now changed. It was chlorine in the front. Now it's in the back. So that would be NS. Very quick way of doing it. So how do they compare to each other? What is the relationship between them? Well, RR, SS, they switch completely. So these are enantiomers. So these are enantiomers, or a pair of enantiomers. What about these? These were switched. S went to an R and R went to an S. So it's the complete opposite. Also, these are enantiomers. However, the question is, what is the relationship between, let's say, 1 and 4, or 1 and 3, or 2 and 3? What is the relationship between them? Well, these would be now diastereomers of these. 1 and 2 would be the diastereomers of 3 and 4, because they are not mirror images. And these would be the diastereomers of 1 and 2. So we always summarize, we always say that the enantiomers are one and 2 and 3 and 4. Again, 1 is an enantiomer of 2, 3 is an enantiomer of 4, but the diastereomers are 1 to 3 is a diastereomer, and of course 1 to 4. And of course 2 to 3 is they're diastereomers. And of course 2 to 4. And finally, I know this is a longer video, but how do we name things? How do we name them? How do we name them? So let's actually name this one using the RR. Well, if you recall, we would number them this way. The R would be the 1, so that would be 1, that would be 2, that would be 3, and that would be 4. So that's butane. We have the name right here. It's 2-bromo-2,3-chlorobutane. Very well. The question is, how do we show, I'm going to use blue. If it's RR, you have to indicate that it was 2R for the bromo and 3R for the chloro right here. This indicates what the bromo, the configuration of the carbon with the bromo is and the one with the chloro is. You can have another one. Let's say, we want to do this one right here, 3. So again, you would say 2-bromo, 3-chloro, butane. I'm going to use blue. So we said it's this one right here, 3. So that would be, let me number them. This is 1, and this one is 3. So that would be 2s, 2, and 3r. And you should be able to tell the relationship even without drawing by looking at these. So we know, again, this relationship is that these are diastereomers. Stereomers. Again, these are enantiomers. So even from the name, you can tell whether they are diastereomers or enantiomers. Enantiomers are the complete opposite. RRSS. Diastereomers are, if you have RR, you would have something like RS. So only one of them would be different. Keep that in mind because the next topic requires as much knowledge of what we've done so far to understand it because it's a little bit tricky.